Welcome back, everyone. What I want to talk about right now is the part that we skipped over last time. I've got my smartboard all fixed up, so hopefully this goes a little bit better. Something you're going to talk about in Physics 20 is called universal gravitation. And now when we think of gravity, we normally think of it as like the Earth pulling us down. And like maybe if you're really stretching, you think like the sun also has gravity, and that's what keeps the Earth in orbit, is technically it's being pulled in. But there is also gravity between the laptop or phone or whatever that you are watching this on right now and your face from 6 inches away. There is gravity between the pencil you are going to use to write your assessment for me and the piece of paper on which you are writing that assessment. There is gravity between anything that has mass. The reason why we don't think about it, and why you probably might not have realized that, is that it is incredibly weak when you have a low mass. So like technically, there's a gravitational force that's pulling you to every other person around you. But every other person around you is like maybe 100 kilograms max if they're a pretty big person. The Earth is like some huge number of kilograms. I don't even know what it is. I think there's like a power of 20 or something on there. So you really only feel the pull from the Earth. However, before the Earth was a thing, it was really important to think about those forces of attraction that weren't quite as strong. So if we think about, like let's imagine that we're back in the classroom and there's 30 of us and we are all of the dust particles that planets and the sun actually became made out of. Let's imagine, or our solar system, let's go with that. Our classroom is our solar system. If there's no Earth, there is no super strong gravitational force all pulling us into one place. So what's going to happen is we're going to be pulled towards each other. And even though that's a weaker force, it is actually going to matter because there is no force that is bigger. So first thing, everything has a gravitational pull to every other thing that has mass. That's what those gravitational forces are. That's also kind of part 2. Part 3 says that if you have a really big or a really heavy thing, that's going to increase the gravitational force. And if you have a really close together, like if two things are really close together, that's also going to be stronger. Let's apply that to what is called the protoplanet hypothesis. This is basically how people or scientists have hypothesized that our solar system was created. And so what they said is we started out with this cloud of gas and dust. Now, in that cloud of gas and dust, some particles are going to be a little bit bigger than other particles. And what that's going to do is it's going to cause the smaller ones to be more attracted to that bigger one because it has a bigger gravitational force. When they start moving like that, well, if I'm a smaller particle and I move towards a bigger one, now there's a gap where I just was. And so things kind of start swirling around, kind of like if you've ever seen a picture of the Milky Way galaxy and it looks like almost a donut that's swirling around. That's the idea here. So it says most of the material, like more than 90%, is going to end up in the middle, which kind of makes sense. If we were playing a game where every time it's like tag, but then like as soon as you're stuck onto one person, you're like stuck together, and then you go around and tag other people. If we were playing that game in this classroom, most of you would end up on one blob, and you would probably be somewhere in the middle. Kind of the same thing how it works with the sun. But there are going to be chunks, so like maybe groups of 2 and 3, that realize if they stick to the outside and just keep running around, they can not get caught up in that big middle clump. And so that would be like your planets, your asteroids, all those other things that are not part of the sun that are still in our solar system. Let's throw some vocab at you. When we have swirling gas and dust, Word for that is nebula. I actually don't have it on here. Okay, this kind of shows what I was talking about with that game of tag though. Start over in that picture right there. And what I want to point out about this picture is that there's no real, like it's all pretty evenly spread out. But as you get out towards these edges over here, that's where we start to lose some of it. But in terms of actually inside of this here, it's all pretty evenly spread out. There's a little bit of a cluster in the middle there. And that's because if you look at this outside here, this only has options to find other stuff over this way because there is nothing over here. But if you're in this middle chunk, well, you have stuff all the way around you, so you're gonna run into more things. That's like our game of tag. You're going to end up being the bigger blob. That then turns into this picture. So we have a bunch more stuff now accumulating in the middle, but there are some patches that there's still a significant amount that didn't get stuck into the middle. And so what would happen is, let's say you are one of these dust chunks right here. You would either be attracted into the middle, like that, or into this bigger clump right here. Now, if you were in this spot specifically, this right here has a much higher mass than this right here. So you are going to get attracted that way. But let's say that you are this dust particle right here. We've got a really high mass, and nothing huge, but it's enough of a mass right there. Except that this distance is way further than that distance right there. So you are actually going to get pulled onto this planet, or asteroid, or whatever it is right there, rather than going all the way into the middle. That is how we end up with planets right here, 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 and the sun in the middle. And because this started as gas that was swirling around, so it's going like this, planets are going to do the same thing. They're essentially that same gas, they've just conglomerated together. Okay, stars. We have a bunch of different ways that we can categorize them. One of the things you'll notice, hopefully as you were doing your astrolabe assignment, is that some stars are brighter than others. And if you took a closer look, you could see that they're also not all the same color. Now that's probably going to be pretty tricky to do without like a telescope or something to see better. But the point is that if you can measure, like let's say you had all the fancy equipment, if you could measure how much light is given off and what color these things are, you can start to learn quite a bit about them. So let's say you have something that is super, super bright, like this over here. That is probably going to have, if we say that decreasing temperature goes this way, that means this is lowest and this is highest. So if you have something that is very, very bright, it's probably going to have a very high temperature. So if it's really bright, you would expect temperature and color correlate. It's probably going to be like an ultraviolet or a blue. Whereas if you have something that's not as bright, so let's look at one of these over here, you're thinking probably less thermal energy, lower temperature, which kind of makes sense. If you look at this picture, like this rectangle right here, that looks like a rainbow. That's your electromagnetic radiation spectrum. And the ultraviolet has the highest energy. The red has the lowest energy. So it makes sense, if heat is just thermal energy, makes sense that it matches up this way. So for your main sequence stars, that's like the typical ones. Our sun is an example of a main sequence star. That is the way that we expect. We kind of have this curve like that. Giants and supergiants behave a little bit differently because they basically just have so much mass. So they are going to be still on the lower end of the temperature spectrum, but because they're so big, they have so much of the reaction going on, I'll talk more about it in a minute, they're still going to have a relatively high amount of light being given off.